I'm a software developer with Juniper Networks. I work there in the routing group. Doing MPLS work, mostly LDP and RSVP stuff. And today I'm going to talk about BGP MPLS VPNs with 2547. Before we start, I need to say that the views that are presented here are of the author and don't necessarily represent Juniper Networks. And in translation, what this means is that this is not a marketing presentation, and this is not going to be vendor-specific either. So the presentation today has two parts. In the first part, we're going to see the basic concepts, the basic building blocks of VPNs. And in the second part, we're going to see more advanced scenarios, hierarchical and recursive applications, carrier, and inter-provider scenarios. And the basis for the entire discussion today is RFC 2547 and the 2547 BIS draft. RFC 2547 is an informational RFC, and it describes the solution kind of like in broad terms. The 2547 BIS draft in the L3 VPN working group in the ITF is the document that actually has the real details for how to implement the solution. And the 2547 BIS draft is authored by a lot of equipment vendors and a lot of service providers. So it's got a lot of support in the industry. So let's start with the basic concepts. And let's see what are we talking about when we say VPNs. So the concept of a VPN is an old concept because the problem that the VPN is solving is an old problem. And what's the goal of a VPN? The goal is we have a customer with several geographically separate sites, and we want to connect these sites and provide the illusion of one network. So what does it look like conceptually? We have this customer green, and it has 4 different sites, and there's no connectivity between the sites. And we want to provide connectivity between the sites, make it look as if it's just one single network. So the first VPNs did in practice exactly what I showed here at the conceptual level, and connected the different sites with point-to-point links, leased lines, frame relay circuits, ATM, and so on. Now what happened was that the customer was responsible for his own routing. So customer routers in one site would peer with customer routers in a different site. Now as the number of sites grows or the connectivity requirements between the sites gets more complex, this places a burden on the customer because he has to handle his routing. Now the business of this customer is not routing. This customer is maybe a financial institution, maybe some kind of retail organization. So now he has to do his own routing, and this places a burden on him. On the service provider side, what the service provider needs to do in such a model is to operate these virtual backbones for each and every one of these customers. So it's not a pleasant prospect for either of them. And in addition to that, when you want to add a new site, it requires configuration not just of that one site that you want to add, but of other sites in the network. So the goal of the BGP MPLS VPNs is to come and solve these scaling issues and to start supporting networks with thousands of VPNs and VPNs with hundreds of sites per VPN. And to do this, the BGP MPLS VPNs move to a different model. It's a model where the peering is between customer routers and provider routers. So let's take a look at the terminology that we have in this model. What we have is the customer sites. These are the green sites here. And at the edge of each customer site, we have a customer edge router, a CE router, which peers with a router on the edge of the provider network. It's a provider edge router or a P router. And the routers in the middle of the provider's network are called the P routers. So what are the properties of the model? The properties are so. CE routers will peer with PE routers, but not with other CE routers. So adding or removing a new site requires configuring the PE router connected to this site only, instead of configuring a bunch of other non-related sites. And we'll see later on that the PE router only needs to maintain routes for the VPNs whose sites are directly connected. So let's see how this works. And rather than just presenting the model, what we're going to try to do here is to try to build the solution from the problem definition. So hopefully what is going to happen in the end that we're going to gain some kind of insight of how we end up with a solution looking in a particular way. So bear with me as we're going to start building this model from the problem. But before we can even start talking about any solution, let's go back and remember what were our goals. Our goal was to do a virtual private network. So I want a network. That means I want to achieve inter-site connectivity. And I want this network to be private. What this means, it means two things. First of all, I don't want traffic from my network to be forwarded by mistake to somebody else's private network. And also, I don't want to see anybody else's traffic in my network. And this network is private. That means, well, I own it. That means I can use whatever addressing I want in my private network. So I want to be able to use private addresses in each one of the VPNs. So let's see how these goals map to the different areas of the BGP MPLS solution. So we said we want to have private networks. We don't want to mix traffic between one network and another. So we're going to see how this is achieved by doing separation of forwarding. Secondly, we said we want to achieve connectivity between all our sites. We're going to see how constrained distribution of routing information is going to help us achieve this goal. And lastly, we said we want to be able to use private addresses in each one of these private networks. So we're going to see how this is achieved by using a new address type and how this new address type is going to ultimately force us to do forwarding with MPLS. So let's take a look at the first goal. And the first goal was to ensure that we don't forward traffic from one VPN to another. So picture this. We have a PE router, and it has several CEs connected to it, and these CEs belong to different customer sites. Now, if the PE router maintained a single forwarding table, then it is quite possible that one customer site would be able to send traffic to a different customer site. So what's the solution? If my problem is that I have just one forwarding table for everything, well, then let's have several forwarding tables, and we'll use multiple forwarding tables and associate each table with a particular site. So when packets come in from a customer site, we're going to identify them based on the incoming interface, and we're going to do our lookup based on the forwarding table that's associated with that site. So these forwarding tables are called VRFs, Virtual Routing and Forwarding Tables, and we maintain one for each site that's connected to the PE. Now, how about achieving connectivity? This was our second goal. We wanted to have connectivity between the sites. So we know that the flow of traffic in a network is shaped by the routing information that is available. So if I want to shape the way the traffic is flowing, I can shape the way routing updates are being sent around. So how can I shape the way routing updates are sent? By doing filtering on them. And we know already that there are mechanisms in place in the routing protocols that allow us to do this kind of filtering. One powerful such mechanism are BGP communities. Why are they powerful? Because we can attach a single community to a large set of routes, or we can attach several communities to one single route. So it's a very flexible mechanism. So let's now go back and see how do we achieve constrained distribution of routing in a VPN. So what is our goal? Our goal is to have all the customer sites have routing information for all the other customer sites, be able to forward traffic towards them. So the CEs are going to advertise to, each CE is going to advertise to the local PE the routes from its side via some routing protocol, and at this point it's not interesting which routing protocol is used. The PE is going to mark these routes with a particular extended community called the route target and advertise them through BGP to all the other PEs in the network. The remote PEs are going to filter these routes based on the extended community and advertising back to the CEs. So what does it look like? Here we have two sides of the customer green. site 1 and site 2. And in site 1 we have the prefix 10.1/16. In site 2 we have the prefix 10.2/16. And we want to forward this, to distribute this routing information between the sites. So what we're going to do, C1 is going to send his route to the PE connected to it. The PE is going to attach a route target to this route on export, route target green, and is going to advertise it to all the other PEs in the network. Similarly, CE2 is going to do the same thing. And so far, everything looks good, except what would happen if now we had two sides of the customer gray that also happen to use the same addresses and also want to advertise the same routes. What we would end up with is now we would end up in the BGP advertisement with two routes for the same prefix carrying two communities. And that is something that we don't want to happen because we don't want to actually start doing route selection on these routes. We actually want all the routes to be distributed. So our problem was that we were having the same prefix with different communities coming from different VPNs. So our problem was that we had no way of distinguishing between these prefixes that actually belong to customer green and customer gray. So the way to solve this is to say, okay, if my problem is that the addresses are not unique, I'm going to make them unique. I'm going to force them to become unique by attaching to the IP address a distinguisher, which is an 8-byte quantity called a route distinguisher, which is going to make this address unique. And the route distinguisher is structured in such a way that it's either a loopback address and an assigned number, or an AS number and an assigned number. And what's important to remember about the route distinguisher is that because of its structure, every provider can assign these numbers independently and they're guaranteed to be unique. So let's revisit the same example from before in a minute and see how VPN IP addresses help us there. So the VPN IP addresses are advertised by BGP in a special address family, and they're only used in the provider's network in order to provide us uniqueness of the addresses advertised. So the translation between VPN IP addresses and normal IP addresses happens on the PE. And bear in mind, the route distinguisher is not used for doing the route filtering and is not used to identify the VPN in any way. It's just an artifact that helps us get addresses unique. So let's see the same example as before with route distinguishers this time. So we have the two sites of customer green and two sites of customer gray, and they're using the same addresses inside each site. And as the PEs attach a route distinguisher to each address, these addresses become unique, and in the middle of the network we have no problem carrying them all. And now what happened is that I exchanged one problem with another. I fixed the problem of the overlapping address space, but I introduced a new one. Namely, I don't know how to forward based on VPN IP addresses. So what happens now is that since there is no way to forward for these special addresses, we need a tunneling mechanism in the middle that will allow us to forward traffic to these destinations. So one very powerful property of MPLS is that it can allow you to do forwarding to destinations for which you don't know how to do the IP forwarding. You put the packet into the label switch path on one end, and you basically determine where it's going to pop up at the other end, regardless of what's the IP destination of the packet underneath. So now what we're going to say, let's do MPLS forwarding for these addresses. So let's see how this is looking like so far. I have this customer green, and he wants to forward the packet to a destination in the second site of customer green. So the packet arrives from CE1 to PE1 on the interface that PE1 associated with this customer green. PE1 is going to look in the VRF that belongs to customer green. It's going to say, okay, destination 10/16 was advertised to me by PE2. So I need to forward this packet towards PE2. It encapsulates it in MPLS and sends it all the way to PE2, where hopefully PE2 will send it off to the correct site in customer green. And this seems to be all right, except if the picture was a little bit different. And we also had a customer gray attached to PE2. What would happen then? The packet will arrive from CE1 to PE1. PE1 would correctly know how to pick the route based on the correct VRF for customer green, would encapsulate it in MPLS. The traffic would arrive at PE2, but now PE2 has no way of picking towards which one of its CEs it needs to forward its traffic. Why? Because the traffic is not marked in any way. The traffic doesn't have any distinguisher that's telling you this traffic belongs to VPN gray. In the routing plane, what we had, we were using these extended communities, the route targets, to achieve a similar functionality. In the forwarding plane, so far we haven't seen a similar mechanism. So the idea is to use a label to identify this traffic as belonging to a particular VPN. And this is also called a VPN label. But think a little bit what actually the purpose of the VPN label is. The VPN label actually allows you to identify which is the next hop on the remote PE which you want to take. So the label is going to be distributed by BGP at the time that BGP distributes the VPN IP address. So now when traffic will be forwarded, traffic will carry two labels, the VPN label and the LSP label. The LSP label is going to be the label that will give us forwarding throughout the provider's core. The VPN label is the label that's going to allow the remote PE to pick the correct next hop for this traffic. So let's see what the picture would look like now. So customer green is going to send a packet towards a destination in site 2. PE1 is going to put a two-label stack on this packet. The bottom label is a green label that was advertised by PE2 at the time that he advertised the route from site 2. And the purpose of the green label is to help PE2 identify that this traffic needs to be forwarded towards CE2. The top label here is the label that's giving us connectivity between the PEs and is bringing the traffic all the way to PE2. So inside the provider's core, we're going to forward the traffic based on the top label only. When the traffic arrives at PE2, the traffic arrives as labeled traffic still with the VPN green label, and PE2 has no trouble knowing that it needs to forward this towards CE2, which is connected to VPN green. Similarly, if we had somebody from site 1 of VPN gray sending a packet, then we would attach a two-label stack, and the bottom label would be a VPN gray label, such that PE2 would know that it needs to forward the packet towards CE3, which belongs in VPN gray. So let's stop a little bit and see what happened. So what is the purpose of the label? The purpose of the label is to identify a next hop. So now my next question is, so do I need one label per route, or can I use one label for several routes? And the answer is, if several routes share the same next hop, then we can use the same label for all these routes. Now let's look what else happened. We have now MPLS throughout the provider's network, and we're forwarding traffic as MPLS throughout the provider's network. And I'm saying we have a label switch path between the two PEs. And I didn't say, is this an LDP or an RSVP label switch path? But since I have MPLS in the provider network, then I also have the opportunity to take advantage of all kinds of MPLS features that are available, such as link protection, fast reroute, standby path, to give the customer more resiliency. So let's see what the model is so far. we've seen that the P routers now don't have to maintain VPN routes at all. The traffic is tunneled over the P routers. P routers don't ever need to know anything about the VPN destinations. The P routers need to know something about the VPN destinations, but only for VPNs that have sites attached to them. And finally, we've seen that we can use overlapping address spaces in different VPNs. So let's take a look now at the routing exchanges that actually happen in the network and the forwarding tables that get built as a result of this, and see how it all comes together. So in all the examples, what we're going to do is we're going to show the routing information flow in one direction in order for us to be able to forward traffic in the opposite direction. And I'm always only going to show one direction only of the routing exchange. So first of all, we know that we need to have MPLS between the PEs. We need for that label switch path between the PEs. So what we see here, we see, for example, LDP advertising a FAC for PE2 throughout the provider's network. And as a result of that, at PE1, we're going to have a route for PE2 with a next hop that is a push label for the label that was advertised by the last guy in the path. Secondly, let's take a look at what route distribution happens from site 2 towards site 1. So C2 is going to advertise the 10.2/16 address towards PE2 via some routing protocol. PE2 is going to take this advertisement. It's going to put a route distinguisher on it to make it unique. It's going to assign a label to it in order to be able to identify the traffic that belongs to site 2 of VPN green. And it's going to attach a route target to it that will allow us to do the constrained distribution of routing in the network. Next, PE2 is going to send this route to all the other PEs in the network. The traffic is going to arrive at, the route advertisement is going to arrive at PE3. PE3 doesn't have any site from customer green attached to it. So he's not going to be interested in receiving route advertisements for route target green. So he's just going to drop this advertisement, not do anything with it. PE1 is going to receive the same advertisement, is going to accept it because he knows he has a site of customer green behind it, and advertise this route towards the CE attached to this site. So let's take a look at what forwarding tables get created and where. So first of all, we have the advertisement between PE2 and PE1 for the route 10.2/16 with a route distinguisher attached to it, and the label 1001. The label 1001 is the way that PE2 is informing everybody, if you want to send traffic to me to VPN green, send it with label 1001 so that I know that it belongs to VPN green. So he's installing a forwarding entry in his MPLS table saying, when I receive traffic marked with 1001, I'm going to send it off on the interface towards CE2. I'm going to send it off on an interface IF4. The same route advertisement is going to create forwarding state also on the remote PE, on PE1. PE1 is going to install a route for 10.2/16 with next hop PE2 and the push label of 1001. Now this BGP route here has a next hop of PE2 that needs to be resolved. Now we've already seen that the LSP that was signaled between PE2 and PE1 created an entry for PE2 with a next hop of push 200. So PE1 is going to be able to resolve this BGP route and create an entry for 10.2/16 with a next hop of a double push label 1001, the label that was advertised by PE2, and on top of it, push label 200, which is the label that was assigned by, let's say, LDP for the PE1, PE2 LSP. And finally, P1 is going to advertise the route towards C1. So C1 is going to have a routing entry saying for 10.2/16, forward the traffic towards P1. So let's see how forwarding will happen. A packet is originated from site 1 for 10.2.11. It arrives at P1 on the interface that P1 associated with customer green. P1 is going to look up its destination in this green table and going to see that it needs to push a 2-label stack on it. It's going to put the 2-label stack on the packet. The packet is going to travel through the core as MPLS based on the top label only and arrive at P2 with one label, that's the label 1001, that's the VPN label that was assigned by P2. Now P2 is going to find the entry in the MPLS table, instructing him to forward traffic with label 1001 on the interface between P2 and C2 as IP traffic all the way towards C2. So what's the summary? First of all, we need to have a full mesh of BGP between all the PEs. Second, BGP is advertising a label along with a VPN IP address, and this label determines the next hop to use when receiving traffic. And thirdly, because we have now the traffic between these PEs is going to be labeled traffic, we need to have MPLS connectivity between the PEs. So what are the concepts that we've seen? We've seen that we can use MPLS to forward traffic across nodes that don't have the routing information for the packet's final destination. These are the packets in the middle of the provider's network, the P routers. And we've seen that we use a label to mark the traffic and use this marking to pick the correct next hop when the traffic arrives at the destination. And the address of the next hop in the BGP advertisement is what provides the coupling between the VPN routes and the internal routing to the remote PE. This was the route resolution that we saw resolving over the LDP route. So now that we've seen how it works, let's take a look at the scalability properties of this solution. So first of all, let's take a look from the customer's point of view. So from the customer's point of view, this is a very attractive prospect because there is just one routing peering, the CEP routing peering, regardless of the number of sites that are in the VPN. So that means that the customer doesn't need any routing skills. The customer doesn't need to operate his own backbone. And this is a very important scaling property because if we're going to have, if we hope we're going to have a large number of customers, then it's less and less likely that these customers will know how to do their own routing. From a provider point of view, it's also quite a nice arrangement because adding a new site requires configuration of one PE regardless of the number of sites. It's a constant number of changes required to add a new site. And route distinguishers are structured so that each provider can manage his own space. And this is maybe at this point not that interesting, but when we'll see the hierarchical applications, you'll see why this is interesting. And PE routers have to maintain routes only for the VPNs to which it is connected, and PE routers don't have to maintain VPN routes at all. And the important thing to remember from this is that there is no single component in the provider's network that has to maintain all the VPN routes. So theoretically, there is no limit to the scalability of this solution. So now, this is all very good, but how do I evaluate a VPN solution when I go shopping for one? So what kind of numbers do I need to look at when vendors come and tell me they want to sell me a VPN solution? So there are two components, right? There are the CE boxes and there are the PE boxes. The CE boxes, we've already seen. The customer is not going to do much routing. He's not even interested in doing much routing. The routing from the customer's point of view can be as stupid as a static route on the PE. So the CE box is not relevant to this discussion. what is the component that is actually interesting and doing all the heavy lifting and making this happen? These are the PE boxes. So if we're going to talk about the scalability of a PE box, let's remember what are the functions that the PE box is performing. So it does several functions. First of all, it maintains all these VPN routes in the VRF tables. Okay? Secondly, it does all these routing exchanges with all the other PEs in the network and with the CEs connected to it. So usually what the numbers for VPN scaling look like is telling how many VRFs a box can support and how many routes per VRF, because this is going to give the total number of routes that the box can support. And the numbers are going to be different depending on what protocols the box is running between the PE and CE. The reason is because different protocols have different requirements in terms of memory, CPU, and so on. So you're going to ask me, so what are typical numbers that vendors advertise? And my answer should be, well, you have to ask the marketing department because we're not allowed to say such numbers, but Juniper, the Juniper implementation, depending on the platform and how much memory you buy and so on, is a few thousand VRFs with a few hundred routes per VRF. So let's take a look at the connectivity models that we can achieve with this solution. So we've already seen that the flow of data is determined by what routing information is available. And who's doing the constrained redistribution of routing information? The PE. What this means is that the customer is not involved in providing the connectivity model, so no expertise is required on the customer, and no configuration is necessary on the customer box. So as you see, like the VPN solution is offloading all this burden of routing and constrained routing from the customer to the provider. Now, the way the PE box is achieving the constrained distribution is through BGP extended communities, through these route targets. And we know already that BGP extended communities allow definition of very flexible policies. Indeed, the policies can be made so flexible that some customers deploy 2547 as a mechanism to constrain access in their network. So, you can think of these financial institutions where people can access some information but not all information. So there are some customers who are doing 2547 in the network just to provide the constrained access. What they used to previously do through access lists, now they can do very cleanly through the distribution of these communities. Because you can constrain it at the level of a single route. You don't have to constrain it, the access to the entire site. So what are the connectivity models that people talk about? There are two main models that people talk about. The first one is the any-to-any connectivity, it's the full mesh that we've seen in all the examples so far. And the second one is the hub and spoke connectivity, where you want to force all traffic from the spoke sites to travel through the hub site. So how is the any-to-any connectivity achieved? The any-to-any, the full mesh connectivity, is very simple to achieve. You have one route target, you attach the route target when you export the route, and you filter on it when you import the route. So everybody is going to see all the routes in the network. How is hub and spoke achieved? Hub and spoke is achieved by using two communities, two route targets, a spoke route target and a hub route target. So the spoke sites are going to export the routes to the hub site using the spoke route target, and the hub site is going to re-export these routes with a hub route target. Then the spoke sites are going to import routes with community hub, and so the traffic will flow from the spoke sites through the hub sites, and I'm sure this was completely unintelligible, so let's look at the example. So we have these two green sites, which are the spoke sites. And we have this one red side, which is the hub side. And what we want to do is we want to force all traffic, even the traffic between the spoke sides, to flow through the hub side. Why would I want to do that? Let's say because that's where my firewall lives. So I can force all traffic to pass through the firewall. So we said we have two communities, community spoke and community hub. So the spoke sites are only going to accept routes with community hub, and the hub site is going to accept routes with community spoke. So let's see the route advertisement from site 2, from PE2, for prefix 1012/24, which belongs to site 2. So this prefix is going to be advertised with a route target of spoke. And it's going to be advertised to all the PEs in the network. Now, PE1 is going to receive this advertisement, and is going to filter based on the import policy he has. He says, well, community spoke, I'm not accepting community spoke, so he's going to drop this advertisement. So PE1 is not going to have a route for 1012/24. However, PE3, which is attached to the hub side, is going to accept this advertisement and keep it in his pocket for now, for the sake of the example. And let's look at the advertisement from PE1 for the routes that belong to the site number 1. So similarly, he's going to send it out with the route target spoke, and PE2 is going to ignore the advertisement, but PE3, the hub site, is going to accept it and keep it in its pocket. Now the hub site is going to re-advertise these routes with community hub. So it's going to summarize them and advertise them out with community hub. So now both the spoke sites are going to accept this route. So when they forward traffic, the traffic is going to flow through the hub route, through the hub site. So far we've seen the basic model of operation of VPN, where the VPN customer is an enterprise with a small number of routes. And in all our examples, we were showing one route, which was the subnet that was used within the customer site. So now we're going to look at scenarios where the customer is himself a service provider. So the VPN customer can be either an internet service provider, or he can be a VPN service provider. And in this context of VPN customer as a service provider, there are two scenarios. The first one is carrier's carrier, when all the customer sites are in the same AS. And the second one is multi-AS operations, or inter-provider backbones, where the customer sites have different AS numbers. So when talking about these hierarchical applications for VPNs, we need to introduce a new concept, the external routes versus internal routes. So external routes are routes learned from peering points or from customers, and they're usually carried in BGP. And internal routes, they include the provider's internal links, including the BGP next stops and the loopbacks, and they're carried in the IGP. So before we can even start talking about these hierarchical applications, let's revise the concepts that we saw previously. So what we've seen so far is that we can use MPLS to forward traffic across nodes that don't have routing information for the packet's final destination. And we've seen that we can use a label to mark traffic, and based on that marking, pick the correct next hop. And lastly, we've seen that the BGP next hop is the glue between external routes and internal routes. So let's take a look at a scenario where an ISP is a VPN customer. So first of all, this scenario is known as carrier's carrier, section 9 of 2547 bis, and this is how people refer to it. They say carrier's carrier in 2547 bis. And it has two sub-scenarios. One where there is no MPLS within the sites, so within each site we forward based on IP. And the second one is when there is MPLS within the customer site, so you can use MPLS to forward within a site. And the goal is the same goal as we had before. We want to interconnect geographically separate sites of the ISP. For example, two POPs that don't have a connection between them. Now, what's the difference between ISP as a customer and enterprise as a customer? So the difference is in the number of customer routes. So in the case when the enterprise is the customer, we have a very, very small number of routes. And it can be as little as one route for the subnet. When we have ISP as a customer, now the routes that this customer carries as his routes are going to be the entire routing table. So what this means is that if I am a PE and I have this ISP connected to me as a customer, I will have to carry as VPN routes the entire routing table for this customer. And if I have several of these connected to me as the PE, then I will have to carry several copies of the full internet table, one for each one of these VPN customers. Okay, so you can say, well, why don't you get yourself a box with more memory then? Well, the problem doesn't end here, because as a PE, I need to advertise these routes to all the other PEs in my network. And internet routes, they tend to flap quite a bit. So this is going to put quite an immense routing burden on me as a provider. So what's the solution? The solution is to say, why don't we let this customer be responsible for his external routes? After all, the business of this customer is routing. He's an ISP. He should know how to do routing. The business of the enterprise customer was, whatever, financial services, something else. He wanted to offload his routing on the service provider. But an ISP as a customer can handle his own routing. Okay. So what does this look like conceptually? We have two POPs of ISP green. There's two sites, site 1 and site 2. And in each one of these sites, this ISP is peering with some peer network and receiving external routes. Now, what ISP green wants at the conceptual level, he wants these two POPs to look as if they were just one single network. So he wants to be able to redistribute the routes that he received on the external peerings through IBGP to all the other guys in his network. So the idea is, why doesn't the transit provider, the VPN service provider in the middle, give enough connectivity to this customer in order for him to be able to accomplish just this, to be able to have these IBGP peerings between everyone and exchange the routes. So as before, we're going to start building this model, and we're going to see what problems we hit along the way, and then we're going to build a solution that way. So, okay. So we said external routes are going to be exchanged via BGP between the two geographically dispersed sites. So if my goal is to establish BGP sessions across the VPN service provider, then what I need to do is I must have routes to the loopbacks of all the other routers in the other POP. So why don't I advertise only the internal routes as the VPN customer routes? So I'm going to advertise all the loopbacks of the routers in each site as VPN routes. And my goal is, the provider doesn't want to carry the customer's external routes. The provider only wants to provide enough connectivity to let the customer do his business. So let's take a look at scenario 1, where there is no MPLS within the customer site. So conceptually, what we're going to have is we're going to have the two ASBRs. They're going to have the external peerings and EBGP. And what we want to have, we want to get an IBGP between these two ASBRs and exchange the external routes. And we want to have a VPN service provide us connectivity to the loopbacks. Now, I'm showing here one IBGP session. In practice, you of course want to have a full mesh of IBGP. So let's take a look at what this looks like. We're going to show the routing information flowing in one direction so that we get traffic in the opposite direction. So, okay. So if I want to have an IBGP between these two ASBRs, then I want to advertise the loopback of ASBR1 as a VPN route all the way to ASBR2. So easy. We've already seen how it's done. We'll have MPLS in the core of the VPN service provider, because we know already we need an LSP between the two PEs. We'll have CE1 advertise the route for ASBR1 to PE1. PE1 will pick up this route, we'll attach a route distinguisher to it, we'll give it a label. The label identifies the link towards CE1, and we'll send it off to all the PEs in the network, in particular to PE2. So PE2 is going to receive this route and install forwarding state for it with a double push label, as we've seen previously. The top label to provide connectivity through the service provider's network. The bottom label is the label that was advertised by PE1. Finally, PE2 is going to advertise this route for ASBR1 to CE2, and the route is going to make its way to ASBR2. Now ASBR2 has a route for ASBR1, and in principle we're able to establish the IBGP session and exchange the external prefixes. So now ASBR2 will have a route for 21/16, which is the external route that was learned in Site 1. And so far this is all very good, but rather an academic exercise, because our point was not to exchange routes. Our point is we want to exchange routes because we actually want to forward traffic for them. So let's see what happens when we try to forward traffic in this model. So let's see that we want to forward the packet towards destination 2111 from Site 2. So we have a route for 21/16 with the next hop of ASBR1, and we have a route for ASBR1 pointing towards CE2, the guy at the edge of this site. So we're going to forward the traffic as IP towards CE2. CE2 is also going to have a route for 21/16 with next hop ASBR1, because you remember we have a full mesh of IBGP. And he has a route for ASBR1 with the next hop of PE2, because that's where he learned the route from. So the traffic arrives at PE2 on the link that PE2 associated with VPN green. So PE2 is going to say, okay, let me look for a forwarding entry for this prefix in the VRF for VPN green. It's going to look in there, and the prefix 21/16 is not going to be there, because all that we exchanged in this routing exchange was the loopback addresses of all the guys in Site 1. Now 21/16 is an external route. The whole point of the exercise was that we didn't want to carry the external routes as VPN routes. So now we have a problem, because we don't know how to forward this packet from PE2. So what's the solution? Well, we're going to apply the same solution that we apply when we don't know how to forward based on the packet's destination. We're going to forward the traffic as MPLS. We're going to tunnel the traffic across all the guys who don't know the IP destination. So who is the last guy who knows the IP destination, the external route? This is C2 at the edge of Site 2. So we're going to extend an MPLS tunnel between CE2 up to where? Up to the first guy on the other side, who again knows how to forward this packet as IP. So conceptually what we're going to have is we're going to have traffic arriving as IP at the ASBR, being forwarded as IP throughout Site 2, being forwarded as MPLS between the two CEs, and again as IP within Site 1. So we're going to have IP, then MPLS, and again IP. So what we need to forward the packet as MPLS between the last guy who knows how to forward it as IP to the first guy on the other side who needs to forward it as IP. And how are we going to achieve this? We're going to set up a label switch path between the remote PEs. And to accomplish this from a practical point of view, what we're going to do is when the PE advertises the VPN routes to the CE, it will also advertise a label for them. So this basically will extend MPLS all the way to the CE. And then we're going to use this label in order to pick the correct next hop on the PE. So let's see how it's done. So the first part of the exchange, we've already seen several times before. We're going to have CE1 advertises a route for ASBR1 to PE1 via some routing protocol. PE1 is going to pick this route, attach a route distinguisher to it, pick a VPN label for it, and send it all the way to PE2. As a result, since it picked the VPN label for it, it's also going to install a forwarding entry saying when I receive traffic with this VPN label, I need to send it out on the interface towards CE1. And finally, the new step is that from PE2 to CE2, we're going to advertise the prefix for ASBR1 with a label attached to it. So let's say that PE2 picks label 2002 and advertises it along with the route for ASBR1 towards CE2. What does this label 2002 mean? What is the meaning that it has for PE2? It means when I get traffic with label 2001, I know that this traffic is actually destined towards ASBR1, and I'm going to forward it based on the forwarding information I have for ASBR1. So the forwarding entry that PE2 is going to install is going to say, when I receive in 2001, I'm going to swap it to the two label stack that PE1 expects from me. The bottom label is the VPN label that PE1 advertised. The top label is the label that's going to give me transit through the core, is the LDP, the label that was advertised by LDP in the core. And finally, CE2 is going to also install a route for ASBR1 with the next hop of PE2 and label 2001. Because CE2 is the guy who actually has to mark the traffic as it travels towards PE2. So these are the forwarding entries that get created. I would like to take one moment and look again at this routing exchange. So remember, I always say we're going to look at the routing exchange from one side flowing to the other side. Just for this once, now picture that we also want to do the similar exchange for routes from side 2 towards side 1. So what will happen then? What will happen is that I'm going to have exactly the same protocols again on these links. So I end up with two protocols running on each link. The eBGP family INET labeled unicast in order to distribute the label for the route at PE2, and the CEP protocol that I didn't specify what it was on the CE1 PE1 link. Well, the question is, can't I use a single protocol instead of using two? And the answer, of course, is yes, otherwise I wouldn't be asking the question. So instead of using some random CEP protocol between CE1 and PE1, we can also use eBGP family INET labeled unicast on this link. But since we don't really need to have a real MPLS label on the link, then we can, what label are we going to advertise? We can pick either label 0 or label 3 to advertise on that link. So in my example, I picked to advertise ASBR1 with a label of 0. So the forwarding entry will be, when I receive traffic with a VPN label that I advertise, swap that label to a label 0. So let's see what the forwarding looks like. So I have the route for 21/16, which next hop ASBR1 on ASBR2. Now I receive a packet with destination 2111, and I want to forward it to the other side. Inside side 2, I'm going to forward this as IP, and the packet is going to make its way all the way to CE2. At CE2, I'm going to find the route for 21/16 with next hop of ASBR1. And we know that to reach ASBR1, we need to send the traffic to PE2, but not just anyway, we need to send it as labeled traffic, with a label that was assigned by PE2, the label that will identify this traffic as destined to ASBR1 in the eyes of PE2. So the traffic is now encapsulated with the label advertised by PE2. It arrives at PE2 with the label that PE2 advertised. So PE2 knows that this traffic is destined for ASBR1. So it's going to swap this label to the label stack that's going to send the traffic over to the correct site on the other side. So it's going to swap this to the double label stack. The bottom label is the VPN label that was advertised by PE1. The top label is the label that's going to give us transit through the core. The packet is going to arrive at PE1 with the top label, the VPN label. So PE1 will know that it needs to send it out on the interface towards CE1. And since we were running BGP labeled unicast on this link, we are going to swap this label to a label 0 in the example that I gave. The packet is going to arrive at CE1, the label 0 is going to be popped, and the traffic will be forwarded again as IP within site 1. So what are the new concepts that we've seen here? We've seen that the label is meaningful on the box that allocated it, on the box that assigned it, because it identifies the next hop to be used for forwarding. So every time we assign a new label, we also must install the forwarding state that stitches the new label that we assign to the correct forwarding state that will carry the packet to the final destination. And what I mean is, I allocate label 2001 at PE2. That means I need to stitch this 2001 label to the forwarding state that I had for ASBR1. So what's the summary for this scenario of ISP as a VPN customer? The VPN provider now doesn't have to carry the customer's external routes in his backbone. He only carries the customer's internal routes, basically the BGP next hops. And this is a big savings from the VPN provider's point of view, because he only carries a small amount of customer routes. We have a label switch path between the remote CEs, and the IP traffic to external destinations travels over this label switch path all the way to the remote PE. So let's see how this picture changes if we have MPLS within the customer sites. And the goal is the same goal. The provider doesn't want to carry the customer's external routes. So what's the idea? The idea is we can use MPLS to forward traffic in the customer sites. So there's no need for all the routers to carry the external routes. So we can rely on MPLS to forward traffic wherever there is no IP route for this traffic. So we need a label switch path between the routers that actually carry the external prefixes. So assuming that we only carry the external prefixes on the ASBRs, then what we're going to have conceptually, we're going to have a label switch path between the ASBRs. We're going to receive traffic as IP at the ASBR, forwarded as MPLS all the way to the other ASBR, and from there on, again as IP. So we've said already there is MPLS within the customer sites. So what we'll have IP coming from the outside, and immediately as the traffic arrives at the ASBR, it gets encapsulated in MPLS. We have MPLS within site 2. We've already seen that we can establish a label switch path between the two CEs, and we have MPLS within site 1. So all that we need to do is we need to stitch these segments together in order to provide conceptually one single label switch path between the two ASBRs. And what we're going to see next is how this is accomplished. So in the previous scenario where the ISP was a VPN customer and he didn't have MPLS within the site, we've seen how to establish a label switch path between the CEs. So now we're going to see how we stitch this label switch path to the MPLS that exists in each one of the sites. So again, we're going to see routing information flowing in one direction and traffic in the other one. So I don't think there is much point of going again on how we establish the path between CE to CE, because we've just seen it. We have LDP in the core, we have eBGP between CE1 and PE1, we have iBGP family INET VPN between PE1 and PE2, and again labeled BGP between PE2 and CE2. All this exchange is exactly the same exchange that we've seen before. And as a result of it, what we end up with the following forwarding entries and with the label switch path between the two CEs. Now let's see how we manage to stitch this to the MPLS in Site 2. So what is my goal? My goal is to have a label switch path for destination ASBR1 within Site 2. So I can accomplish this by using the same mechanism that I used before. I can accomplish this by having an iBGP labeled unicast session between CE2 and ASBR2, advertising a route for ASBR1 with next hop CE2, and the label, let's say 4001. What's the purpose of this label? The purpose of this label is to, when CE2 receives traffic marked with this label 4001, CE2 must know that this traffic is actually destined for ASBR1. So as a result of the iBGP exchange, on ASBR2, we now have a route entry for ASBR1 with next hop CE2 and the label of 4001. Now if I want to send traffic to ASBR1, I need to be able to have a label switch path that will carry this traffic all the way to CE2, since the traffic is going to be labeled traffic. That's not a problem, because we've seen that we have MPLS within the sites. So assuming we have LDP within Site 2, what we have LDP advertising FEC for CE2 all the way throughout Site 2. So ASBR2 will have a route for CE2 with a next hop of, let's say, push 500. So now ASBR2 can resolve the route for ASBR1 by installing a route that has a double push, push 4001 as a bottom label and 500 as a top label. Again, what does this mean? The top label is the label that's going to give us transit within Site 2. It's the LDP label that's going to carry the traffic between ASBR2 and CE2. And the bottom label, label 4001, is the label that's going to inform CE2 that this traffic is actually meant for ASBR1. Now let's apply. Okay, so let's take a second look at this picture. What we have is we have a two-label push at ASBR2, and one label identifies ASBR1, and the other label identifies the path to CE2, which is the router that actually injected ASBR1. Now let's take a look at Site 1. So again, let's apply the same principle that we've seen before. We don't want to have several routing protocols running. We want to have the symmetry of routing protocols in both sites. So we're going to have an iBGP INET labeled unicast session also between ASBR1 and CE1. The ASBR1 is going to advertise a route for himself with a label of 0, because we don't really need a label for this route. Because we already have LDP within Site 1 advertising the FEC for ASBR1 all the way towards CE1. So basically on CE1, what we end up having now is we end up having a route with a double push label. The top label is going to be the LDP label from the LDP route in site 1, and the bottom label is the label that ASBR1 advertised, and since he really didn't have to advertise a label for this route, we're using a label 0 in this case. So what do we have so far? So far, we've seen how we stitch the MPLS between site 2 and the CE2 to CE1 label switch path. And the last step is how to stitch the path at CE1. So we know that between CE1 and PE1, we're running eBGP INET labeled unicast. And in the previous example, we were advertising a label 0 there because we didn't really care if traffic was coming in as IP on this particular link. But now we do care because we need the traffic to arrive as MPLS on this link because we need to continue to forward it as MPLS within site 1. So we're going to advertise a real label for it, let's say label 3001. And label 3001 means when I receive traffic with label 3001, this is traffic destined for ASBR1. I want to swap this label to the label stack that will carry this traffic to ASBR1. So we'll have forwarding status says, when I receive traffic with 3001, I'm going to push a double label on it, label 0 and label 100. So these are the forwarding entries that got created, and let's see what happens to a packet as it arrives into this network. So if we have a packet for 2111 that arrives at ASBR2, ASBR2 has a route for 21/16 with a next hop of ASBR1, and it has a route for ASBR1 with a double push label, label 4001 and label 500. The packet is going to be encapsulated as MPLS with a 2-label stack. The top label will carry the traffic all the way to the exit of this site. The bottom label is going to identify this traffic as destined for ASBR1 for this guy at the edge of the site. We're going to swap the label with label 2001, which is the label that identifies this traffic as belonging to ASBR1 from the point of view of PE2. And PE2 is going to swap this label with a double label stack that's going to carry the traffic across the backbone and to the correct PE. And the PE is going to, based on the VPN label that he advertised, swap the label with the label that identifies this traffic as belonging to ASBR1 from the point of view of CE1. And finally, CE1 is going to swap this label to the label stack that's going to carry the traffic to ASBR1. So what have we seen so far? We've seen that we can use MPLS to forward traffic in the customer side. So given that we can use MPLS to forward traffic in the customer side, then we can hide the knowledge of external prefixes from everybody except the ASBR, and then we'll forward the traffic in a label switch path between the two ASBRs. Okay, so in all the examples that I've seen so far, we were using labeled BGP inside the sites as a mechanism to advertise labels. The question is, can we use LDP instead? And the answer is yes. So we've seen that within Site 1, we didn't really need the BGP session for ASBR1 because we already had an LDP route for ASBR1. We had LDP running within Site 1, advertising effect for ASBR1. So CE1 had a route for ASBR1, an MPLS route for ASBR1. The question is, can we trick LDP to do the same work for us in Site 2? The answer is yes. What we need to do is we want CE2 in Site 2 to advertise a FAQ for ASBR1, and we want this FAQ to be propagated throughout site 2. There are two things that need to change in the LDP protocol in order to do this. First of all, the guy who injects the route, he has to advertise a true label for it rather than a label 3 or a label 0, which LDP would normally advertise. That's fine, because all the vendors already implement such an extension. Secondly, what we need to do, we need to inject a route for ASBR1 into the IGP in site 2. Why do we need to do that? Remember, LDP is not a routing protocol. It's a signaling protocol. So he relies on the IGP in order to decide, am I allowed to install forwarding state or not? So we need at every hop along the way in site 2 to have a route for ASBR1. So if we inject these routes in the IGP, then we can establish this LDP route between starting from CE2 for ASBR1. Now, there are two things that may not be so desirable in this solution. One is that if site 1 belongs to a different provider, this is not the case. In this case, we're talking about the same provider. But if he belonged to a different provider, I wouldn't be too keen in having to carry his internal routes in my IGP. The second thing is that if I need to have the route for SBR1 in my IGP, and since I know this route from BGP, I will need to do some redistribution from BGP into my IGP. So these are the drawbacks of using LDP as a solution, and there's currently a draft in the ITF on this topic that tries to solve this, and it's authored by Juniper, of course. So if anybody is interested in discussing it afterwards, I'd be happy to talk with them. So if we use LDP instead of BGP, what we end up with is with a single label push at the SBR2 instead of the double label push. Okay, so far we've seen an ISP as a VPN customer. Let's see a scenario where the VPN customer is himself a VPN service provider. And the goal is simple. Let's provide connectivity for geographically dispersed site of a VPN service provider. What does it look like? We have a VPN provider green. It has two sites, site 1 and site 2, and it has two customers, customer red and customer blue. And what it lacks connectivity between these two sites. So it cannot run his VPN stuff because he lacks connectivity. So we want the provider in the middle to give the connectivity to achieve this. The problem is that the provider in the middle has no interest having to carry the routes from this red customer and blue customer in his network. Because if he's going to start doing that, then he's going to carry a whole bunch of VPN routes for all these VPN customers that he has. So the approach is the same approach that we took for ISP as a customer. We let the customer do his own routing, and all that the provider will provide is will provide connectivity for the loopbacks and enough connectivity to allow him to forward traffic. So what does it look like conceptually? Conceptually, we're going to have an IBGP session for the external VPN customer routes, and we're going to have an LSP between the two remote PEs. So this is the same, exactly the same picture as the ISP as a customer scenario with MPLS in the customer sites. The differences are that we're exchanging VPN IP routes instead of plain IP routes, and this will eventually require us to do a 3-label push when using label BGP. So we'll take a brief look at how this looks like from a routing forwarding point of view. We've already seen in the previous example how we can establish an LSP between the two remote sites when we want an MPLS LSP between them. So if we have the LSP, now we want to run IBGP INET VPN session between these remote PEs, mimicking exactly what we were doing in the plain vanilla scenario at the very beginning of the discussion today. We want to exchange these customer reds routes as VPN IP routes with some VPN label, let's say label red, between these two sites. So PE3 is going to attach a route distinguisher to route 10.1/16 from customer red. It's going to attach a VPN label red to it. It's going to send it through IBGP to PE4. Now PE4 has a route for PE3 with a double label push from the exchanges that we've seen in the previous scenario, the exchanges where we established the label switch path between PE4 and PE3. So what PE4 is going to do, he's going to install a route for 10.1/16 with a 3 label push. The bottom label is going to be the label red that belongs to this red customer, and the other 2 labels are going to be the labels that are going to provide connectivity to PE3. And that's all that there was to that. Lastly, we're going to talk about VPNs services across AS boundaries. And the reason this is interesting is because there are actually quite a few providers whose backbone is partitioned among different ASs. So the other scenario where this is useful is that the VPN sites are connected to different providers. So what does it look like? We'll take a look at 2 sites. One belongs to VPN provider green and the other one belongs to VPN provider gray. And we have the same customers, customer red and customer blue, which attach to these 2 separate providers. I choose to mark them as 2 separate providers. You can think of them as the same provider but with different AS numbers. The problem is that now we can't run IBGP anymore between the remote sites. And there are several solutions for this problem, and they're described in 2547 bits in section 10 as option A, B, and C. And this is how people refer to them: option A, option B, option C. So option A is the simplest option to understand. And let's just skip the talk and look at the picture. Option A, what it says, is like, okay, we have these PEs. On each PE, we have a VRF for each one of these customers. Why don't we just run eBGP between the VRFs? So we'll have several interfaces between these PEs. Each interface will be associated with one of the VRFs, and then we'll exchange the VPN routes directly as normal IP routes via eBGP through these sessions. Now it's a little bit more complicated than this because normally the PE boxes are not the ASBRs. So the solution in the draft says, okay, what you need to do then, you duplicate this VRF state on the ASBRs. And then you run multiple eBGP sessions and exchange all these VPN routes. Well, what's the problem with this approach? The problem is exactly that. We're exchanging all the VPN routes. It's a lot of routing exchange. On top of that, we have multiple eBGP sessions that need to be maintained in order to accomplish something like this. And given that the PEs are normally not the ASBRs, then the ASBR must carry a large number of routes and VRF state on the ASBRs. So, okay, so let's refine this solution. And this is refined in option B. And what option B says, well, leave the ASBR alone and have the PE routers use IBGP to redistribute the VPN IP routes to the ASBRs. So now the ASBRs don't have to maintain per VRF state. And ASBRs are going to use eBGP to redistribute the labeled routes to an ASBR in the other AS. So now, instead of multiple eBGP sessions, we have one eBGP session, and instead of having the ASBR maintain all these per VRF states, it just maintains one big table. Now, what's the problem with this approach? Okay, let's see first what it looks like. We'll have IBGP within the site to the ASBR, and we'll have eBGP between the ASBRs. It still requires exchange of all the VPN routes, and it requires us to have an inter-AS LSP between the two PEs, because previously we were exchanging IP routes. Now we're exchanging these VPN IP routes. We're expecting to receive labeled traffic from the other side. So we need to have an LSP across AS boundaries. And an LSP across AS boundaries is not something well defined. It's being defined now in the ITF. So the problem with both option A and option B is that all the VPN routes are exchanged. So the scalability of the solution depends on the number of VPN routes that we have in a site. And option C comes to solve these scalability problems by using the same approach that we've seen before. Don't carry all the VPN routes. Carry only enough information, carry only the internal routes. So you use eBGP to distribute the VPN IP routes between the PEs, and the ASBRs only exchange the internal routes to these PEs. So what does it look like? It looks exactly like this. We have eBGP for the external customer routes between the PEs, and we'll have an LSP between the PEs, and the VPN routes will be the routes for the loopbacks of these PEs. So this looks exactly like VPN provider as a VPN customer, and the same routing exchanges will happen. The difference are that the two sites are now attached to different ASs, so we're using eBGP instead of IBGP between the customer PEs. So normally when people say option C, they mean not necessarily an inter-AS scenario, but any scenario where instead of exchanging the routes, you exchange the routes to the loopbacks, and you do the trick of forwarding traffic as MPLS throughout the domain where the route is unknown. So what we've seen today, we've seen the plain vanilla VPN scenario, and then we've seen the more advanced topics where we're using hierarchical application or recursive VPNs. But the same mechanism was used throughout. And the mechanism was you use a label to mark the traffic, and you use this marking to pick the correct next hop. And that's it.